Okay, let's continue. Just now we stop here. Well, we try to do a lot of the breakdown and analyze this Tn. And we have the A, Tn divided by B, and we say the problem is this part. And for this part, we are assuming that the aftermath, after the divide and conquer is a linear algorithm. And the linear algorithm could be, we have two sorted sublists, and now we want to combine them together into a final sorted list. And we say this is a linear algorithm. However, in the real world divide and conquer algorithm, well, this part may not really be necessary, but if there is a aftermath part of the divide and conquer recursive algorithm, we can't just assume that the aftermath is a linear algorithm. And this brings us to an even harder question. How do we come up with a general cookbook to solve any divide and conquer algorithm? And of course, we have the A and B, and A and B are good. However, for this part, the Cn, the aftermath cost of the divide and conquer, we have to take it as any polynomial. It could be log n, it could be constant, it could be n squared, or anything, right? So now the major change from what we just seen to the master theorem is we are expecting the aftermath cost to be a function of n. So we are solving a problem like this. So A, Tn divided by B, but now the Fn will be the additional aftermath cost. Okay? So how do we solve that? Well, there are still, similar to what we have seen before, there are three cases. Well, but for those three cases, I'm not gonna prove the equation after equation to show you how do we get here. And but I'm gonna show you what is inside the box of the master theorem. And that is, there are three cases: case 1, case 2, and case 3. And for the case 1, and if we can prove that Fn is O n to the log BA minus a epsilon. Oh, what does that mean? Well, for this epsilon here, well, we are saying the epsilon is a small positive value. Okay? Well, if Fn is a big O n log B n to the log BA minus a small positive epsilon. This epsilon can be something really small, like a 0.001, or could be 0.5, or could be 1, could be 2. Well, if you are able to find a small positive epsilon that works, and then that should be enough. So that's the case 1. And number 2, if you can prove that the Fn, this part, is exactly theta n to the log Bn, n to the log Ba, and then this will be the case 2. And for the case 3, it is a little bit more complicated. So there are there are two parts of the case 3. Number 1, you have to prove that Fn is omega n to the log Ba plus a small positive epsilon. And in addition, you also want to prove that A of the Fn divided by B is smaller than a constant C Fn. Okay, for a large n. So the case 3 will be the hard part. Okay, so well, this is still very dry, I understand that. So let's see a few examples. So number 1, we have the Tn as 9 Tn divided by 3 and plus n. Okay, so how do we figure out what case is that? So number 1, we want to grab the A, we want to grab the B, and we want to grab the Fn. So A is 9, B is 3, and Fn is n. Okay, so what's next? So next, how about we grab this part, n to the log Ba. So what is n to the log Ba? So n log 3, 9 will give you n squared. Okay, so now we have n to the log Ba as n squared. And for the Fn, we have that as n. So can we prove we are in case 1? So to say we are in case 1, and how about we assume that epsilon, the small positive value, is a 1. So if the small epsilon is a 1 and n to the log BA, which is 2 minus a 1 here, so you are going to have n here, right? So Fn is n. And then O n to 2 minus 1 will give you 1 again. So n is O n. That is true. So case 1 applies. And you may ask, why did you pick epsilon as a 1? Well, I can say, how about we use an even smaller value? How about we pick epsilon to be 0.01? 0.01. And what are we going to have? So now we have the n powers 2 minus 0.01. What are you going to get? You are going to get n powers 1.99, right? So Fn, which is n, is O, n powers 1.99. Is that true or not? Yes, that's still true, right? So to be safe, you can pick a really small epsilon value, and you don't have to pick 1, you can pick an even smaller. Well, in this case, I pick 1 to make this case easy, but usually when you are considering this case, you want to pick an even smaller epsilon value. Okay, so anyhow, we are able to prove that, well, Fn is O n to the log BA and minus the epsilon, and we are using the epsilon as 1. So in other words, we can say n to the log BA grows faster than Fn, because n to the log BA is n squared, and n squared grows faster than Fn because Fn is n itself. So in this case, what's the solution? The solution is theta n to the log BA. So theta n to the log BA will give us the theta n squared, and that is the time complexity of this recursion. Okay, that's fast, right? We don't have to write a full whiteboard of the equations in order to figure out this recursion. Well, we can use the case 1 of the Master Theorem, and then this is solved. Okay, so how about case 2? So let's see another example. So for this one, what is A? Well, A is 1 because there's no number here. And what is B? So B is 3 divided by 2. And what is Fn? Fn is 1. This means that is a constant value, right? So let's figure out what is the n to the log BA. N to the log BA will give you n power 0, which is a 1. So n to the log BA is 1. And Fn is also 1. So case 2 applies because Fn is a constant. And theta n to log BA is also constant. So that is definitely case 2. And then how do we solve case 2? Case 2 is n to the log BA and then log n again. So we want to say, okay, to translate this part, this means n to the log BA grows, Fn is theta n to log BA, and that is true. So that is theta n to log BA and log n. And for the n to the log BA, that is a constant. So, well, this algorithm is n to the log BA. So, this is theta log n. So this is the second case solved. And again, after we are able to figure out this is case 2, and then we just apply the master method, and then the recursion is solved. Okay, so let's move on and see the third problem. So for the third problem, again, we want to figure out what are the A, B, and Fn. So A is 3, okay, good, and B is 4, that's also good, and for Fn, that is n to the n log n. Okay, so let's see what is n powers log BA. N powers log BA will give you n power 0.8. N powers 0.8, and for this one, this is n log n. Well, and for this case, it's obvious because this one grows slower than linear. And for this one, n log n, it grows faster than linear. So it's kind of obvious that, well, this part, Fn, grows faster, Fn grows faster than n to the log BA, or n log BA grows slower than Fn. Okay? So we kind of figure out the first part. And how about the second part? We want to test this. So A Fn divided by B is smaller than C Fn. And C has to be a value greater than 1. Is that true? So let's plug in the number and then the Fn and see. So what is Fn? Fn is n log n, right? So we want to plug in the A here, B here, and the Fn is n log n. So if we try to massage this data a little bit, and then can we have this part solved? So we want to prove this part, and then this C has to be a value smaller than 1. Can we have that? Okay, so we start here, and then we extract the 3 divided by 4 here, and we have the n to the log n divided by 4. And this value is smaller than 3 divided by 4 and multiplied by n log n. And what is n log n? N log n is exactly the Fn, right? So I want to substitute this n log n with the Fn, and what do you have? You have a small constant value multiplied by Fn, and what is the C value? C is 3 divided by 4, and that is 0.75, which is smaller than 1. So we have proved two things. So number one, n powers log bn grows slower than Fn. That's the first thing. And number two, well, after we plug in A and B and the Fn, we are able to prove that A Fn divided by B is smaller than C Fn, and the C value is 3 divided by 4. That is a small positive value smaller than 1. So after we have proved those two parts, we can say this case can apply the case 3 of the master method. Okay, so let's move on. So we can apply the case 3, and then how do we do that? So for the case 3, that is theta Fn. And in our example, what is Fn? Fn is n log n, right? So we can say, okay, this recursion is a theta n log n algorithm. We are done. Okay, so well, you see the power of the master method. You don't have to write a lot. You only have to figure out when you have a recursion, you only have to figure out which case applies to this recursion. If you can find one case applied to this recursion, and then you just plug in the master method and use the specific case, and then the problem will be solved. Okay, so well, let's do a very quick review of the sorting. So far we have talked about, well, formally talk about two sorting algorithms. We talk about the merge sort. And what feeling do you have about the merge sort? Do you feel merge sort is fast? So think about that. We also have insertion. Well, by the way, what is the big theta of insertion? Well, we are talking about the worst case. So for the worst case, for the insertion, that is AO n squared. And how about merge sort? Merge sort, we say that is n log n. So n squared versus n log n, which one is faster? Okay, you will, well, by saying it is faster, we mean when the n is larger, which slope is slower? Okay, that is the n log n, right? N log n takes less time. Or when we have an even larger n value, the increase will be smaller, so the running time will be faster. So the merge sort is a faster algorithm. But what else? How about, other than the time complexity, how about we also talk about the memory? So do you like the merge sort or the insertion sort when you are considering the memory consumption? Or let me ask in another perspective, merge sort versus insertion sort. Which one requires extra memory space? which one can store the values in place? Well, how about take the insertion? For the insertion, we are shifting the value to the right side, and then we are plugging in a new value to the right place, right? That's the insertion sort. So for the insertion sort, do we have to create extra space? And you may say, yes, we have to create actual variable names. Well, that's true, but that variable can be reused. But how about, so my short answer is no, for the insertion sort, you don't have to spend a lot of the extra memory space. And how about merge sort? If we have two lists, how do we merge them together? When we merge those two sorted sublists together, we have to create a new empty list. So we do the cherry picking either from one list or another list, and then we move that down to the new list. That's a new list, right? And we are merging two lists of the n divided by 2 to a final sorted list of n, and that is a space of additional n item list required. So for the merge sort, we do have to spend extra memory. Okay, so well, the next thing on our agenda will be heap sort. So we want to combine the advantage of both of those algorithms, and we have an even better sorting algorithm. Okay, so that's the topic for the next lecture. And for the reading, and today you do have a lot of reading to do on this book. Well, we have the sections 2.3.2 talking about the master method, and then you also need to read the section 4.1.3 and 4.5, see more applications of the master theorem. Okay, so enjoy reading this book, and I will see you later. Bye.